All right. This problem, we've got a light string attached to a large block, mass 4m, passes over a pulley with negligible rotational inertia, is wrapped around a vertical pole, radius r. It's then released from rest, and the block descends. The string unwinds, and the vertical rod that's attached to the apparatus rotates. The apparatus consists of a horizontal rod, length 2L, with mass m attached at each end. The rotational inertia of the pole and the rod are negligible. So some vocabulary. Our pole is our vertical, our rod is horizontal, and the length of that rod is 2L. A, determine the rotational inertia of the rod and block. So we're looking for the rod and the block attached to the top. Because if we look at this from above, we've got mass here, and this whole thing is 2L. So it's rotating about its center like this. Whenever you have this, you're going to have a mass here and a mass here, and a radius and a radius. So that means you have two moments of inertia. And by definition, our moment of inertia equals the sum of mr squareds. So if you have an m1 and an r1, you're going to square that, plus m2, r2, square that, and so on and so forth. In this case, both of our m's are equal. They're both m. And both of the r's are equal. It's going to be half of our 2L, which is just L. So our moment of inertia equals ml squared plus an ml squared. Our moment of inertia is 2ml squared. We don't have to do any deriving, nothing crazy for this problem. Even though it says determine the rotational inertia, that may have frightened you away, but I hope you'll see that it's not that bad. Part B, determine the downward acceleration of the large block. All right, so we have to figure out what is exactly happening here. We can't just solve for acceleration using our net force. Instead, as this block goes down, it's pulling here. So we have this tension that's holding our 4m mass up that is also pulling this rod. Or excuse me, this pole. I'm mixing up the vocabulary. So it's pulling on this pole. So that pole is spinning in circle. So because that's happening, the fastest that this will be able to accelerate is going to be the angular acceleration of this pole. Alpha, fish thing. Okay, so we have to find out what is alpha. And it's not a fun process. The likelihood that you're going to see this on the exam in 2020 is very low because there is so many steps and so many equations that I'm about to use. So no, you don't need to know these steps, but yes, I do want you to watch this and review these concepts in your mind because, again, AP loves having rotational stuff on their tests, so it's probably going to show up somehow, some way. Okay, so let's go ahead and get started. Where do we start? We're looking for an acceleration, so let's start with our free body diagram of our 4m mass. We know that's Fg, which is going to be 4mg, right? And then we know we have tension. This is moving downward, so there is a net acceleration in the down direction. So there is some kind of acceleration downwards. So we'll start out with our F net equals the stuff that makes it go minus the stuff holding it back equals ma. What's making it go, what's positive, and what's negative? I would, in this case, normally you would say tension is, or up is positive, down is negative. I'm going to flip it around for you because it is moving downwards, so I'm going to take Fg to be positive. So stuff that makes it go is the force of gravity, stuff holding it back is tension equals ma and it's not M. M is these tiny little masses. Instead, what is actually moving? 4Ma. Okay, so let's solve for tension here. We're going to get tension equals Fg minus 4Ma. And then go even further. I said Fg equals 4mg. 4mg minus 4ma. And I'm going to just kind of sit on that and wait around before I can use that again. So again, the tension is pulling here. It's pulling to the right. And it's causing this to rotate. So the agent of force is the tension in the string that is causing it to rotate. Whenever you have a force causing something to rotate, vocabulary term is torque. Force causes something to rotate is a torque. And we know torque equals I alpha, and it also equals Fr. All right. Oh, wait a second. Here's alpha. That's what I said we were going to be looking for, because the fastest that this is going to be accelerating downwards is going to be alpha. It's going to be as fast as this pole can angularly accelerate. It's our angular acceleration. So there's that. F, what is F going to be? Tension is providing that force. Capital T, tension. All right. R is going to be that distance here. I don't know that it's the same thing as L. It looks like it probably is, but I'm just going to keep it as R for right now. Moment of inertia. Remember, we already defined moment of inertia to be 2ml squared. Oh, good. So we're just going to plug this in and then solve for alpha. So we have 2ml squared alpha equals 4mg minus 4ma times r. Divide by 2ml squared. And we're going to get our alpha to be 2gr squared over L squared plus 2r squared. A lot of algebra there that I skipped to. I skipped down to the answer for you, but rework it, practice your algebra skills. It's not going to hurt for sure. So that's it for B. That by far is the hardest part of the whole thing. It may seem like it's an innocent question with only 7 words or 8 words or whatever, but it's obviously got a lot going on. The key, of course, is recognizing that the downward acceleration has to equal your angular acceleration of that pole, because that's as fast as it can go down. Part C, when the large block has descended a distance d, the instantaneous total kinetic energy of the 3 blocks, compare the value of 4mg. Okay, so it's asking about the total kinetic energy after this block has gone down some distance d. I know this is a separate experiment. Just forget about those little strings right there for a second. So the kinetic energy of each of these blocks has to be the same. And it says justify your answer. Okay, from step 1, make sure you check the correct check mark. Put your check mark in the correct spot. Without a check mark, the readers aren't going to grade anything beyond. And even if you get the check in the wrong spot and you have the correct answer, you may still get a point. So make sure you put a check if there's a checkbox. Not sure that there will be because of the format of the test, but anyway, there it is. So Why is it equal? There's no non-conservative forces. Remember, a non-conservative force is something that does work on the system, that transfers energy out of the system. We're neglecting friction, we're neglecting air resistance. The pulley is frictionless. So there's no non-conservative forces acting here. So that means all of the energy has to be contained within the system. So it's asking, when the large block, how does the instantaneous total kinetic energy of the 3 blocks compared to the value of 4 mg? Well, that's just asking mgd. That's just our potential energy. Ug equals 4 mgd, right? And our energy in the beginning has to equal our energy in the end. Our energy in the end equals K1 plus K2 plus K3. 3 different blocks, 3 different kinetic energies. They all equal to 4 mgd. So in words, if you're asked to do this, I would say, because no non-conservative forces are present, conservation of energy applies, and the total potential energy in the beginning has to equal the final kinetic energy, in words. So that's it. On to D. The system's now at rest. The string is rewound around the pole to bring the large block back to its original location. The small blocks are detached from the rod and suspended from each of the rods using the string of length L. The system is again released from rest, so the large block descends into the apparatus, rotates. The small block swings outwards, and as shown in experiment B above, this time the downward acceleration of the block decreases with time after the system is released. So when the large block has descended a distance, D has the instantaneous total kinetic energy of the 3 blocks compared to part C. So now we have this string here added in, and that string is important because it allows these masses to go up. If you can picture this before 4m starts to fall, then you just have m and m. And then afterwards it starts to rotate, and these things move outwards. The faster it moves, the higher they're going to go. So you can see there is a small change in height here. If there is a small change in height, then that must mean these blocks now have some sort of potential energy. If they have potential energy, remember there's no non-conservative forces. No non-conservative forces. And because there's no non-conservative forces, that means energy is conserved. So we're not getting that extra energy from outside the system and moving the blocks up, but instead the energy is coming from within the system. So remember, all of our energies in the beginning have to equal all of our energies in the end. Energies in the beginning started with Ug with height D, and then now we have kinetic 1 plus kinetic 2 plus kinetic 3 plus U1 plus U2, UF2. There should be a 2 there. Okay, so now you can see the energy is spread out among more different. So that must mean the instantaneous total kinetic energy has to be less. And the justification is all of this into words. Because there's no non-conservative forces present and energy is conserved, the blocks now having potential energy is taking away from the kinetic energy of the block going down. Pretty cool problem, pretty cool situation. B was tough. Everything else I feel like you should have down by now. Hopefully you do. If you don't, please ask questions. We are running out of time. All right, have a good day.